So today, what I'd like to talk to you about is logic gates. Now, in computer science, logic gates are a fundamental thing to be able to understand, and all it really boils down to is whether something is true or on. We can refer to true as being on, or false or off. And you may know that in computer science we can use on and off to represent binary numbers. So I could have on being 1 or off being 0. And in Minecraft, there is this thing called redstone. Redstone allows you to kind of put these kind of electrical cables down, and you can either power them on or you can power them off. And you have certain electrical devices such as this lamp, and when I power it on, it turns on, and when I power it off, it turns off. Now that means, that game mechanic in Minecraft means that you can actually build a working computer in the game, if you had the time and the expertise, of course. But as a simple example, I could use these lights to represent a number. So I could, maybe if I click that one on and these two. Okay, now starting from the right hand side, I've got 1, 0, 1, 1. Or sorry, I should have started from the left hand side. I've got 1, 1, 0, 1. Now this here represents the number 1. This one represents the number 2. This one represents the number 4. And this one represents the number 8. And if you know anything about binary, that shouldn't come too much of a surprise to you. Now this isn't a video about binary, so I'm not going to go into the detail of how that works, but needless to say, I've got the number 8 add 4, which is 12, add 1, which is 13. I've represented the number 13 using redstone in Minecraft, okay? Now we can do more exciting things with this, so I'm going to get rid of these, and what I want to do is talk to you about gates and how gates work. Now, gates are like a fundamental part of computers, and these are what allow us to build really complex circuits that can do really impressive things. But these gates are kind of as simple as it gets. Well, no, this binary digit is as simple as it gets. Okay, so having an on state or an off state is as simple as it gets. Making it ever so slightly more complicated is gates, and then we can combine gates to get proper logic circuits, which in turn do the kind of weird and wonderful things that your computers can do. So this is our fundamental principle. I can have something in an on state, I can have it in an off state, and we can refer to that on and off as 1 and 0, or true and false. And we're going to be working with true and false today. So true is on and false is off. And so here we can see that our input, if we think of this in terms of an input over here and an output over here, I have an input of true. So I've put true into this, and the electrical signal goes over to here. Now in Minecraft, when you feed a redstone torch, I've got a redstone torch here, when you feed a redstone torch power, it turns off, but a redstone torch gives power naturally. So if I give the redstone torch power, it will actually turn off. So at the moment, I have a NOT gate because my input is true, but the output is false. And you can see this lamp here that I've got set up in my output area is off. Now, if I change my input to false, we can see that my output is now true. So we can see this light is on, we can see the power coming down here from the redstone torch all the way down, and I have a true output. So this is true, and that's false, and then the input is false, and that is true. So we've been able to make a logic gate in Minecraft, the NOT gate. And this NOT is essentially just the opposite of whatever you put the input in. So if I'm not wearing a hat, then wearing a hat is false. So that was a really bad example. So when light is on, input light is on, output light is off, and when input light is off, output light is on. True and false. Input true, output false, input false, output true. Get the idea? Okay, let's take it up a notch then. This here is an OR gate. Okay, now an OR gate means that I have two inputs. Okay, let's call them A and B for ease of use. And if I turn on A, you can see the output is on. So if I have true here and false, so sorry, true or false, because it's an OR gate. So if I have a true here and a false here as my two inputs, I have an output of true. Now if I was to shift this and turn this on, so I have false here and true here, I still get an output of true. And if I have both on, I still get an output of true. The only time in an OR gate when I get an output of false is if both are off. So you can see there that that is false now when both of these are false. As long as one of these is true, light works, and if both of them are true, the light still works. So that's our OR gate. At least one of these has to be true. If I turn them both off, we have false. So that's an OR gate. Now we're going to go to an AND gate. So an AND gate is just like an OR gate, but instead of having just one on, turning the light on, if I do that with my AND gate and turn it on, I get no output there. Okay, so my AND gate has to have both its input A and its input B on, true, to give a true output. So they're both off and they're false. One on, one true, one false gives false. One true, one false gives false, but both true, and I get true. And so this is our AND gate. ANDs take an input, and both inputs have to be true in order for this output to be true. And then lastly, we have the XOR gate. So XOR in one kind of string of letters, no spaces. The XOR, the X in XOR stands for exclusive. So what we mean by this is if I turn on, it's just like an OR gate. So let's go back to our OR gate and remind ourselves. So if I turn on this, on, yep. If I turn on this, on, good. And if I turn on both, great. Okay, exclusive OR means that if you have both on at the same time, if both things are true, then it's false. And that's the difference. Only one can be true. So if I've got this here true and this false, I've got an output of true. If I have this false then and this false, then it's false. And if I just have this true and this false, then I've got an output of true. But if I put both of them to true, my light goes off and I have no signal. So my exclusive OR has to have two inputs, and one of them has to be false and one of them has to be true. It can't have two trues. It's exclusive. It's just a pure OR. So imagine going to the shops for your dinner and you were told to get a curry or a pasta dish. Okay, you wouldn't come home with both if you were going out to get dinner. Okay, so you would have an exclusive OR where you do one or the other. You don't do both. Now let's make this a bit more interesting just to finish off. So let's grab some TNT and just recap what we've gone through. So let's replace these with explosive blocks. Oh dear, I think I walked over a cave there. Okay, so to start with, our NOT gate. Now hopefully you can remember what this is doing. So we have a true signal here. So our true signal means that we've got an output of false in our NOT gate. Okay, very simple, it's just inverting. So when we put an input of false, we get an explosion, and that is a true output. Boom. So we do false and we get true. In here, only one of these has to be on, or both, in order to get a true output here. So at the moment we're at false, false, and a false output. But if I turn one of these on, I get a true output. Beautiful. Okay, and so that is our OR gate, and I can turn this on and it doesn't affect the circuit. I can turn this off and it doesn't affect the circuit. As long as one of these are on, or both, it doesn't matter. That's our OR gate. Now we're going to go over to our AND gate. Now for our AND gate, to make this TNT explode, what am I going to have to do? Well, I've currently got an input of false and false, and I've got an output of false. The output would be true if the TNT was exploding right now, which it's not. So if I turn this one on to true, I've got nothing. Okay, my AND gate is not putting out any signal. But if I was to turn the second one on to true as well, let's just turn this one off and turn this one on. No, still no change. So if I was to put them both to true, now we've got a true output, and we can see nice dramatic reveal that that is true. And lastly, we've got our XOR. So what I'm going to do here is I'm just going to break a bit of the dust that takes the signal up, and I'm going to turn these both on. Okay. Now having both of these on, both of these set to true, does not give us a true output. Only one of these being on will trigger this TNT here, because this is an exclusive OR. Only one can be true. And so what I'm going to do is I'm going to turn one off, and now that I've only got one true, our output is true. And there we go, there you have it. Logic gates in Minecraft, and just to recap what we've got here, we had our not, we had OR, we had and we had exclusive OR. And I've tried to draw the diagrams for and not, but I think I might need to try building them at a bigger scale because it didn't go too well. But the symbols for OR and XOR, I would like you to go and kind of have a look and see what they are. Make a note of these symbols and make a note of their truth tables as well. So a truth table essentially is, let's build one. Should we build one very quickly? This was unplanned. Okay, so let's do a truth table for a not. So I'm going to say, let's do something like this. Cool, and then we can hide a lever on the back. Lovely. Okay, so for our not gate, this is my Minecraft truth table. Okay, so when my input is true, my output is false. Let's denote these with different coloured walls. So let's grab some white wool and some black wool. So I'm going to say white is input and black is output. Okay. So when my input is false, my output is true. And when my input is true, my output is false. And so you can imagine this being in a table where I have the kind of the heading input. Let's really go to town on this. So let's pop this here, pop there, and let's jump in. Can I search here? Yeah, great. Let's grab a sign, and let's pop a input here and an output here. And we could represent these with ones and zeros as well. So in your table that you draw, you would have yourself a 0 representing off here, and you would have a 1 representing on here, and then you'd have a 1 and a 0. And these are the only states that this gate can be in. The input can either be true or it can be false. We only have one input on a NOT gate, and so we've got a very limited amount of inputs and outputs that this can be. However, if we were to think about our OR gate, we have two inputs. So I'm going to do another here, pop that there. So we have two inputs, and let's pop some levers on those. So now we can have false, false, true, true. We can also have true, false, and false, true. So I need to go up a little bit on this and extend this. So let's go bosh, 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 and let's pop our signs back in. So this can be input A, and this can be input B. So we've got two inputs, input A and input B. Let's pop our lever on the back to turn these on and off. So one of those and one of those. Okay, lovely. These aren't in order. Let's change that. I can just change it by clicking the levers. So let's start with zeros, 0, 0, and then do 0, 1, 1, 0, and then 1, 1. Great. And then let's just build our output stack up a little bit. So we're going to have a block what am I doing? Black wool. Redstone lamp, black wool, and this is going to be our output. Cool, so let's just think about this. So if we've got true or true, then this is going to be true. If we've got true or false, then this is going to be true. If we've got false or true, that's going to be true. And if we've got false or false, that's going to be false. And so this is our truth table for our OR gate. Okay, these are the 4 combinations of inputs that we can have: false, 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 true, true, false, or true, true. And these are the outputs that we would get given those inputs. So if we were to input these signals into our gate, then these are the results we would get. And this is how you can write a truth table. Obviously, if you were writing this by hand, you would have kind of written your column headings, and then instead of drawing redstone lamps, you would just use 0 for off and 1 for on, or 0 for false and 1 for true. And you would do it that way. Or you could do it with false and true, but it tends to be, a truth table tends to use 1s and 0s to represent true and false. So let's just quickly reconfigure this for an AND gate. So this is an OR gates truth table. Let's have a look at what an AND gate would be. So with an AND gate, both have to be on for the output to be true. It has to be true and true for the output to be true. So true and false would actually give us a false output in our AND gate. And false and true would give us a false output as well. Ooh. And false, of course, would give us a false output. So you can see here in our output column, there's only one condition where we would get a true output, and that is if both input A and input B, are true. Okay, so this add this equals, let's do a little okay, so true add true in an AND gate equals this. And we can do the same with these up here as well. I'm really regretting my choice of block here, but we'll roll with it. So that add that equals that. Let's fill these in. So we're going to go there, there, there. Oh wait, I just want to do it all, don't I? Yep. Okay, and then let's pop these in. That adds that equals that, and that adds that equals that. Okay, lovely. So these are our inputs and they are our outputs. And now what we can do is start thinking about our exclusive OR. So we've already done a truth table for NOT, for OR, and for AND. Now let's have a little think about exclusive OR. Now exclusive OR, let's just go and remind ourselves about how it works. I'll use a redstone lamp just to save blowing everything up. So exclusive OR, we have one input true and we have an output of true. We have 2 inputs true and some. Okay, I was missing some. We have 2 inputs true and we have an output of false. 1 input and we have an output of true, and no inputs and we have an output of false. So over here on our truth table, we want false and false equals false. Yep, sure. We have false and true equals false. No, that's not true. That needs to be true. So false and true equals true. True and false, or true or false should I say, equals true. But if they're both on, if they're both true, then it does not equal true. It equals false. And so we have an output here, a truth table here, where if we have input A and input B both as true, then we get an output of false. So the only 2 conditions when we get a true output on in an exclusive OR is when one of the inputs is on and one of them is off. One of them is false, one of them is true. Okay, it's the only time we get an exclusive OR. Hopefully this has been helpful. This has gone on a little bit longer than I thought it would, but hopefully you enjoyed. And maybe I'll think about how I could work Minecraft into more computer science videos. Cool, sweet even.